Okay, for this lesson, we are going to cover motion in 2 dimensions. So we've been working with 1D, meaning things have only been moving east-west, or they have been moving north-south. They have been moving sideways, or they have been moving vertically. But we know that's not an actual reality. We know things can move both sideways and vertically at the same time. So that's when we get into 2 dimensions. So we call that 2D. So before we can really get into studying into 2 dimensions, we're going to get into and cover the concept of vectors, specifically in 2D. So 1D motion moves east-west or north-south. We solve these algebraically by picking a positive direction and adding horizontal or vertical movements together. Main word here is the or, okay? It's kind of like one or the other. Okay, so it's horizontal or vertical movements together. Vectors describe motion moving in an east-west and a north-south direction. So these 2D vectors of 2D motion will be in both directions, sideways and vertically. Now, I know this kind of reads as in vectors are only applicable to 2D. That's kind of how that kind of reads when I'm reading it out loud here. But it's not. Vectors are also applicable to 1D because vectors um, is a scalar quantity or a vector quantity, right? So vectors are just a magnitude and a direction. So we can use vectors in 1D, but we are going to really study the use of vectors in our 2D motion. So how do we draw a vector specifically in 2D? So draw a displacement vector 25 kilometers with the direction east 30 degrees north. So what you're going to do is we're going to focus on the direction. Okay. Now maybe let's take a moment here and just study. So a vector is essentially just an arrow that shows the direction. Now you have the tail part of it, and then you have the tip or the head part of it. Okay. That's it. And essentially the length of the line tells you the magnitude. So the length equals the magnitude. Okay. So this is draw the displacement vector 25 kilometers east, 30 degrees north. So how we draw this is, so this is north, east, south, west. Picture yourself on a graph. So what you're going to do is you're going to go east. So you're going to go along the east line, and then you're going to make a turn 30 degrees to the north. That's kind of how you draw that vector. So you're going to go from the origin, and you're going to go through that line. Okay? We don't have to make it that long. Okay? That's the vector. And then we have this being our 30-degree angle. Now, what if I had number 2, a displacement vector 5 kilometers west? So it's literally just 1, 2, 3, 4, 5. Okay, and that would be 5 kilometers. This would be 25 kilometers. Okay, now technically number 1, the length of number 1, that vector, should be 5 times the length of number 2, but we're just running out of space there. Okay, so number 2 is just straight to the west. Now, when we add vectors, okay, so if we're going to add 2 vectors, we add them tip to tail. So remember up above here, I explained the vector. So the length of the arrow tells you the magnitude of it. So the longer the arrow, the bigger the magnitude. You have the tail end and you have the tip end. So what we do is we add them tip to tail. So if I was going to add these 2 vectors together, the first thing you're going to do is draw the first one. So I'm going to do number 1 plus number 2. So the first vector plus the second vector. So the first thing is we're going to start off from the origin and we're going to draw our first vector. There's our first vector. That's our 30 degrees right there. Okay, so this is 25 kilometers. Now I have to take my second vector, which is going straight across to the west. Now I have to take the tail end of that and attach it to the tip end of my first one. So when you're adding vectors, you're adding them tip to tail. So then you're going to go from the tip part here, and you're going to go straight across 5 units. 1, 2, 3, 4, 5. That's my 5 kilometers. So now technically, if we're going to do this a little to scale, it should be about 1/5 of the size. So it should be something like that. Okay. If we're going to try to draw it somewhat to scale. That's my 5 kilometers west. Now the answer to this is connecting the tail part, so where you started to where you ended. That's the answer. So that red arrow is the answer of adding two vectors together. So that red one is the answer of 1 plus 2. Okay. Now if I'm going to subtract two vectors, so I'm going to subtract vector 1 minus vector 2, what we are really doing is adding the negative version of the second vector. Okay. So the negative version of the second vector is the opposite direction. So if I'm going to, the negative means going the exact opposite direction. So my second vector was going straight west. So in this case, the opposite direction of west is east. This is the negative of 2, the second vector. Okay. So what we're doing is, if I'm going to do 1 minus 2, I'm really getting my first vector and then adding the negative version of the second vector. So I'm going to draw first thing I'm going to do is I'm going to draw my first vector. Like that. That's my first vector. Let me put this on this side. That's my 30 degrees. Now I'm going to add the negative of my second vector. So instead of going west, this one's actually going east. Once again, if we can draw this to scale, should be small. There we go. Now connecting from where you started to where you ended, that's your answer. That red one is 1 minus 2, which is also equal to 1 plus negative 2. So subtracting vectors is literally just adding the negative version of your other vector, okay? So that's a little lesson and review on vectors and how vectors work and how we add them together. Now that's if we wanted to create vector diagrams. Really, a method that we're going to use often in this course is solving questions algebraically, meaning not using exact diagrams. So we can create these exact scale diagrams, and you're literally just going to get a ruler and a protractor and measure everything. But what we can do is solve things algebraically. So we can essentially use, as you can tell here, we're just creating essentially a lot of triangles. So we're going to use a lot of trigonometry to solve these algebraically. The way we're going to focus is using vector components. Okay, so this works for a lot of different problems. So if we have a vector, if you look at this diagram here, we have a vector A. Okay, that red line, vector A going up and to the right. Now, if you look at that vector, you can say that vector is moving a little bit to the right along the X and a little bit up along the Y. So what we're going to do is break this vector down into its components, into its X component and its Y component. So we are going to use SOHCAHTOA. Okay. So if this is my angle that I have, that's my opposite. This is my adjacent, and that's my hypotenuse. Your hypotenuse is always right of your opposite of your right angle. So AX is going to equal to A sine theta. Okay, so the value of your X component is going to be A, your vector, magnitude of your vector, times sine theta. And then your AY, when you use SOHCAHTOA, breaks down to A sine theta. Oops, sorry, I was solving for X here. This is cos theta. When you do SOHCAHTOA, that'll be cos. And then for your Y there, it'll be sine theta. Okay, so what we are often going to do is break our components down into its individual, break our vectors down into our individual x and y components. Okay, so let's here have an example here. So a flight from Toronto to Vancouver is 4,100 kilometers west, 25 degrees south. Determine the components of the displacement. So I'm going to draw this vector. So I always pretend like I'm actually seeing it on here. Okay, so I'm going to draw, so it's going west and then 25 degrees south. So if you're going to draw it, it's probably a little too much. Kind of something like that. So this is going to be 4,100 kilometers, and this is the west 25 degrees. Okay, so what we're going to do is we are going to break this down into its x and y components. So this is going a little bit in the x and then a little bit in the y. So we'll call this displacement. So our displacement in the x is going to equal to 4,100. Now, if you do this, this is the adjacent, so it's cos 25. Okay, so when you do that, 3716. Okay, and then if you do the y, so your displacement in the y is going to equal to your 4,100. This is opposite, so it's sine 25. This is 1733. Okay, now just for sines, let's say everything up, to the right and, to the left and down is positive. So both of those will be positive numbers. You have full control over which direction is positive, but we're going to say which direction is positive. So let's say to the left is positive and let's say to the down is positive. So those stay as positive numbers. Just to show you a little bit different scenario that can arise, instead of this, so every vector has two possible directions. So if you looked at that, that's 25 degrees. So you see this 90-degree angle here? That would make this 65 degrees. So we could have written this as 4,100 kilometers. Now we could have gone south 65 degrees west. It's the exact same vector. It gives you the exact same diagram. So what we can do here is draw it out. So south 65 degrees west, and you're going to get the same looking vector, but it's the 65 degrees that was given to you. So now when you draw this, we technically went vertical and then, oops, that's a little too long. And then we went across this way. That's how we kind of got that vector. Okay. Now why I'm showing this to you is I don't want you to pick up some bad habits. This is the y part and this is the x part. Okay. Now notice in the x, this is 4,100. The x here is the opposite. So it's going to be 4,100 sine 65, and this is going to be 4,100 cos 65. And the angle changes, so we will get different numbers. They won't be the same numbers as above. So 4,100 sine 65. That's 4,100. So you get your same answer of 3716 for your x, and your y is 4,100. 1733. You get your exact same answers. Okay. So I just don't want to get into a habit of always y being sine and x being cos. It's very common for you in a rush of a question to do that because it's often the way angles are given, but not always. So yeah, just wanted to show you, be careful. Y is not always sine. X can be sine, just all depending on the information you're given when you draw your vector. Okay. Now, finding total displacements. So total displacement is when you're having multiple displacements at once. So you're changing position, or when you're having multiple displacements. So when we're having multiple, specifically when we're having multiple displacement vectors. So when adding two displacement vectors, or I should say two or more displacement vectors. So this becomes really useful when you have two or more, specifically more, displacement vectors to calculate your total displacement. Because remember, for displacement, it's your final position minus your initial position, or it's equal to your first displacement plus your second displacement plus your third displacement, so on and so forth. All those are vectors when you're adding those displacements. So there's one version you can do, or there's the second version, right? So in that second version, we're adding a whole bunch of different vectors. So depending on how many vectors you have, you can go back and you can do your scale diagram like we did over here and just keep adding and adding and adding and adding and get a really weird shape. So it's no longer a triangle. Or we can follow this method of using vector components. So when calculating total displacement, what you want to do is step one, break each vector into its vector components. So every displacement vector you get, break it into its vector components. Then two, that stands for, that's sigma dx, sigma dy. That means summation of all displacements in the x and summation of all displacements in the y. So take all your x components, add them together, and then take all your y components and add them together. Then what you're going to do, this is a very important part, is I'm going to call this 3a and I call this 3b, is make your new triangle. Okay, so for example, you're going to have your answer of delta dx, and then you're going to have your answer of delta dy, whatever positives or negatives. That is your delta d total. Okay, so if you notice, this is you're going to draw the triangle. That's going to give you a right angle triangle. So then you're going to use Pythagorean theorem, as in step 3b says, to find your magnitude of your hypotenuse for your total displacement. And remember, your total displacement is still a vector, so we need a direction. So we have to find that angle. Okay, you always find the angle from where you start, not at where you end. Okay. So we typically just use tan, but you can use whatever SOHCAHTOA you want. So here's an example. Okay, a boat travels 3,200 kilometers east, 30 degrees north, and then travels 150 kilometers south, 58 degrees west. Find the total displacement using components. Okay, so I have one vector here, and then I have another vector here. So I'm going to call this delta d1 and call this delta d2. So what I'm going to do is draw out delta d1. So it's east and north. So if you were to draw this out, east and then 30 degrees north. So this is my 320 kilometers. This is my 30 degrees. So I'm going to break it into its components. This is going to be my delta d1x, and this is going to be my delta d1y. So delta d1x is going to be 320. Now this is my adjacent, so cos 30. So when you do that, cos 30 is half. Oh, there's 320. 277. Okay, let's say up and to the right is positive, so that's going to be positive 277. Delta dy is 320 sine 30. That's going to be half 160, and that's up, so that's positive. Okay, so I broke it into its components there. Now what I'm going to do is draw my delta d2, my second displacement, which is 150 south, 58 degrees west. So you're going to have south 58 degrees west. This is going to be 150 kilometers. South 50, that's my angle, 58 degrees. There you go. So this is my delta d2y. This is my delta d2x. So this is going to be 150. Now this one's cos 58 because it's the adjacent side. This is going to be 150 sine 58. And 27. Okay. Now it's down, so down is negative in our case, and then to the left is negative. So these are negative numbers. Okay, just because for our direction purposes. So that's step one, break everything down into its components. Step two is do the summations. So I am going to do the summation of all the displacements in my x, which is delta d1x plus delta d2x. So it's going to be positive 160 and then minus 127. When you do that, you're going to get 33, positive 33. And then you do summations of your delta dy's, which is delta d1y plus delta d2y. Oops, sorry, I did the wrong one here. This is 277. So when you do that, it's going to be 150. Okay, sorry, I made a little mistake there. So 160 minus 79.5 is 80.5. Okay, positive. So now what I'm going to do is draw my new triangle. So we're moving on to step 3, which means make the triangle. Now, it doesn't matter if you use your x or your y first. It's totally your choice. You still get the same answer. So what I'm going to do is you just pick a starting point. Now you can do x or y. Now I have x written down first, so I'm just going to do that. That's 150 positive. So positive in the x was to the right. So I'm going to do 150. That was in kilometers. Now this one is going to be 80.5 positive, which is up. So you're going to add them tip to tail. So it's about just over half the size. Okay, I like to try to kind of draw my sketches to scale. Now this is going to be your final answer right there. This is your total. So now this is just Pythagorean theorem. So your delta D total is the 150 squared plus 80.5 squared square root. When you do that, you get 170 kilometers. Okay, so that's going to equal 170 kilometers. And then you need your theta. So we typically use tan theta here because our opposite is, so TOA, opposite over adjacent. So it's our delta dy, 80.5 over 150, or depending on how you drew it, it could be 150 over 80.5. It just depends if you drew your other triangle. Because what you could have done is, from our starting position, you could have used your y first and then your x. But you get the same answer either way. So it's really important you draw your triangle because your math has to add up, right? So if you did that one and when you solve for that triangle, your answer would have been 150 over 80.5. So when you get these two angles, they're supplementary to each other. So this one is, oops, 28.2 degrees. But if you were to do the other one, it should be 190 minus that. Sorry, 90 minus that, which is 61.8 degrees. So you see, so they work out. So it's either 61.8 degrees or this is 28.2. So I'm going to stick with the one that I got. So my final answer, your total displacement, is going to be 170 kilometers. Now for us, we're going east 28.2 degrees north. That's your final answer. If you used it doing the red triangle, your answer would have been 170 kilometers, but you went north 61.8 degrees east. You see the different way of writing the direction. So that's why it's really important to include your triangle to make sure that your final answer actually matches up with all your math. Because what happens is when you actually do the diagram, when you actually do your math, you actually calculate for the wrong angle. So it's very common to actually switch up these the degrees because you're not drawing a triangle properly. You're not really following through with all your work. So it's very easy to just create the wrong TOA ratio and mix up the degrees. So you always want to include your triangle and always show your works to make sure that you are calculating the right angle. So when you give me the final direction, it's the correct one. Okay, so that's a brief introduction to motion in 2D, and we're going to continue with some more examples in the next part of the lesson.